Hello, Calculus. These are the video notes for the mean value theorem. So the mean value theorem says, let f be a continuous function over the closed interval a to b and differentiable over the open interval a to b. Then there exists at least one point c in the interval such that the derivative of the function at the point c is equal to the slope of the secant line over the interval. And I'm adding some English words here instead of just reading these algebraic expressions out loud to you. Now, if you look at a picture, this is just a demonstration of the mean value theorem and what it's saying. So right here, you've got your orange line from A to B. This is a secant line. And a secant line is just a line that connects 2 points on a function. And since the ordered pair is b comma f of b and a comma f of a, we know that the slope formula is output minus output over input minus input. So when I see the expression f of b minus f of a over b minus a, then the words I'm thinking in my head are slope of the secant line, instead of just reading the symbols aloud to myself. Now this gray box here, a to b, just indicates the interval that we're looking at the function at. And if you check out the black dotted line, you can see that the black dotted line is tangent to our function, which is kind of a purplish color, because a tangent line is going to hit the function at 1 point within the interval instead of crossing through at 2 points. And so C, I'm pointing to it, C is actually the x coordinate, so this really should say C comma f of c, since this is the point on the function. And the derivative at c is that instantaneous velocity, or that slope of the tangent line. So we're basically saying that these slopes are the same because these lines are parallel. And the mean value theorem says if your function is continuous and differentiable over a closed interval, then there exists a point within that interval where you can create a slope tangent equivalent to the slope of the secant line. So how do we use this mean value theorem? Example 1. For f of x equals the square root of x over the interval 0 to 9, show that the function satisfies the mean value theorem, and therefore there exists at least one value c in the interval, such that the derivative of the function at c is equal to the slope of the line connecting 0 to 9. Find these values guaranteed by the mean value theorem. So think about the square root of x function. We know that it's continuous. We also know that over the interval 0 to 9, it's differentiable. Remember, to the left of 0, the function does not exist. So 0 to 9 is within the differentiable realm. With that being said, we are going to solve our expression. So we're going to find the derivative of the function. We're going to find the slope of the secant line for the endpoints of the interval, and then we're going to set those equal to each other to solve. Let's start with the derivative. Can I just erase the prime? So what I want to do here is just rewrite the function with a rational exponent so that my derivative, and by this point you may have memorized the derivative. Sometimes that happens, sometimes we just go through it each time. Here's our derivative. So pause there, save that for later. Then we need to know the slope from 0 f of 0 to 9 f of 9. So let's evaluate f of 0. If you plug in 0, the square root of 0 is 0. And if you plug in 9, the square root of 9 is 3. So the slope is going to be 3 minus 0 over 9 minus 3. Oh, sorry, I'm already simplifying. 3 over 6, which is equal to 1/2. So now we're going to set these equal to each other in the hopes that we can find our value of c. So we're going to do 1 over 2c to the 1/2 power equals 1/2. And you might already be able to see this. The only way for this 1/2 to equal this 1/2 is if c is equal to 1. But let's go ahead and finish the actual solution. Times 2 to both sides. Reciprocate the function. So if you reciprocate the left-hand side, and if you reciprocate 1, and then square both sides. C is equal to 1. And that's because the derivative of the function at c is equal to 1/2, and the slope of the secant line is also equal to 1/2. Next example is going to be velocity, so we're going to take a real-world context, and we're just going to apply the mean value theorem and think about how each part relates to real life. If a rock is dropped from a height of 100 feet, its position t seconds after it is dropped until it hits the ground is given by the function s of t equals -16t squared plus 100. Determine how long it takes before the rock hits the ground. Now, it may not seem like it, but this is actually a bounded interval. You have the beginning at time 0, and then the whole problem is over whenever it hits the ground. So we've got a bounded closed interval. We have a quadratic function, which is continuous and differentiable along its entire curve, which means it'll be continuous and differentiable over this interval. And we just have to solve to see when the interval ends. So hitting the ground means that the height of the rock is going to be 0. And so we've got 16t squared equals 100. T squared equals 25 over 4, if you're simplifying. And then for a square root, we do have a plus or minus, but a negative time doesn't make sense in this context, so we're only going to stick with the positive solution, which is that the rock hits the ground 2.5 seconds after it's dropped, and that gives us a bounded interval from 0 to 2.5 seconds. Next, we're being asked to find the average velocity of the rock when the rock is released and when it hits the ground. So average velocity is also known as your slope. Your slope is an average here. So we're going to find the slope of the position from the beginning to the end of when the rock has been dropped. So the ending is at 5/2, and the beginning is at 0, and then the ending position is 0, and the starting position is 100. And if we're going to write this in notation, we're basically doing f of b minus f of a over b minus a, but we're inputting these variables. So we're going to have s at 5/2, since the function is s of t, minus s0 over 5/2 minus 0. And that's our notation there. Well, that gives me -100 divided by 5/2. Reciprocate and multiply gives you -200 over 5, which simplifies to be -40 feet per second. And at this point, I like to just make sure logic, right? The rock is falling, so the velocity is negative since it's moving in a downward position. And we're good there with logic. Last question for this example. Find the time t guaranteed by the mean value theorem when the instantaneous velocity of the rock, so its velocity at the exact moment from 0 to 5/2, is equal to the average velocity of -40 feet per second. So rewriting the equation, we have s of t is equal to -16t squared plus 100. We're going to find that derivative, which is s prime of t, -32t, and then the 100 has a derivative of 0. And so we're going to say -32, I keep forgetting the 2, is equal to -40 feet per second. Divide both sides by -32, and we get 40 over 32. And that simplifies to be 5 over 4, or 1.25 seconds. So 1.25 seconds after the rock has been dropped, its instantaneous velocity is equal to the average velocity of the entire trip. This is the conclusion of part 1 of the mean value theorem, where we just introduced the mean value theorem and showed how it can be applied both with context and without.